We're going to do sections 3.7 and 3.8. But before we get started, I want to make a clarification on problem 3.87, which is the homework problem that I did on Vodcast number 10. We were talking about a free jet problem, essentially, with a plug that was shaped like a cone inserted in a pipe, and then the water being squirted up around this conical plug in a free as two free jets, or not as two free jets, but as free jets all the way around the plug. So I drew the plug with the free jet of water, which we're told has a thickness of 0.02 meters. When we got down to the calculation for area, I used this formula, which is correct, but I don't think I was really clear about where that comes from. Where it comes from is this circle going around the circumference of the cone, which has a height of 0.02 meters. So if we take this area that the water is squirting out around, what we find is that it is a very narrow rectangle where the length is actually the circumference of the circle, 2 times pi times r. That would be these terms. The height of the rectangle is 0.02 meters, so that the area of the rectangle, or the area at state 2 that the water is coming out through, which we use to find the velocity, is the width times the height of that rectangle. So 0.02, 0.02, 2 pi r, 2 pi r. And those together constitute that second area. So when I went back and I looked at the Vodcast, it was quite unclear to me what I had actually done. So I wanted to make sure to clear it up before we got started with section 3.7. All right, so having said that, we're going to move on to section 3.7, and we're going to talk about some different concepts, but basically these are very practical hydraulic concepts of the hydraulic grade line and the energy line. What we're talking about here is we equate the energy terms in the Bernoulli equation to physical or actual elevations. And as you recall, in our previous discussion, we talked about the fact that the terms in the Bernoulli equation could be written as pressure, or they could be written as heights. And that height, if we write them in terms of height, that we call that head. So we have pressure over gamma, specific weight, which we call pressure head. And the units of that, of course, will be in feet, inches, whatever, the dimensions of length. We also have the velocity head, which is, once again, when we did the numbers, you could see that that's in dimensions of height. And we also have the elevation head. And together, the sum of those equals the total head. So when we work with this idea, your authors, if you think about it in terms of an elevation, here's a simple statement that has far-reaching ramifications. Water runs downhill, or water seeks its own level. But what this really means is if you have a certain, let's say you have a pipe that's running water and it's running downhill. If your energy level starts right here and you equate the energy to an elevation, that water will never pick up any energy unless you put a pump or a turbine in it, right? So that elevation is actually the total energy in the line. Now there are some limitations on this, which we'll talk about for section 3.8. Namely, you're going to have some frictional losses in the line, but we are losing that idea right now. We're just talking about what we started with, and we're not going to gain anything. So the total energy is going to be at the same elevation. Now, if you remember velocity head, v squared over 2g, as the water runs downhill, it's probably going to pick up velocity. So we have another line that we draw, which is called the hydraulic grade line. And the hydraulic grade line is just the difference between the total energy and the dynamic head, or v squared over 2g. Now, I'm going to show you a better picture of this. I'm going to flip over to the podium PC because I'd like you to see something from Engineer's Toolbox. And basically, if you do a quick Google search on hydraulic grade line and energy line, you'll come up with this website called the Engineer's Toolbox. And I would really like you to consider using this when you need a quick reference in the future. So basically, we already know it goes back to our original premise of this entire chapter. What we're studying this entire chapter is the Bernoulli equation. And you see at the top that we have P plus 1/2 rho v squared plus gamma h. And it tells you that that's constant along a streamline. Now, it's a little bit different here because in our equation, when we write it in terms of head, we divide each of those by the specific weight. But these are in pressure terms. So if we go down a little bit to this place and we see we've divided by gamma, and we have an expression for the head, the pressure head, the velocity head, and the elevation head. And they're told that those are constant along the streamline and that their sum is h, which is total head. So it tells you that the total head is the sum of these three things. And as you look right here, you see that we have a graph of the energy line and we have a graph of the hydraulic grade line. Well, what is happening, if you think about this, when you have no difference between the energy line and the hydraulic grade line? Since the difference between them is the velocity head, when the energy line and the hydraulic grade line are at the same elevation, that means that the water is not moving. It has a velocity of 0. It's like here it's in a tank. Here in this diameter pipe, we have a fixed, relatively fixed v squared over 2g term because the velocity is going to be approximately the same as long as it's incompressible in this pipe if it's the same diameter. So my hydraulic grade line is going to be some distance below the energy line. When we narrow up the pipe, what has to happen? Well, the pipe, in order to get the same flow rates, because we're going to have the same Q if it's an incompressible fluid, going to have the same volumetric flow rate, definitely going to have the same mass flow rate. That means that it's going to have to speed up. If the area gets smaller, because Q is equal to V times A, so Q has to stay the same. If A is smaller here than here, that means that V has to be greater. So what that means is that the hydraulic grade line is going to dip down pretty significantly. So that's just a graphical representation of the difference between the energy line and the hydraulic grade line. Now, at the bottom here, oh, it's not really at the bottom, but in the next section, we talk about the piezometric head and the energy line. The piezometric head is the sum of the pressure and the elevation head. Okay, the energy grade line we've talked about a little bit, and we've talked about the hydraulic grade line. So if you look at the pressure head, P over gamma, and the H, or the elevation head, our authors use the variable Z, but we're just talking about a height in this case. that's the hydraulic grade line. So the piezometric head basically is the same as the hydraulic grade line. And it just describes here the piezometric head is the flow that can be measured through a flat opening parallel to the flow. That kind of a measurement, the flat opening parallel to flow, is called a piezometer. So anyway, one of the reasons I wanted you to see this is just because Engineering Toolbox is such a great site for sort of quick refreshers of these different types of ideas, but also because I wanted you to see the graphical representation of the energy line and hydraulic grade line and what they mean. And it really is kind of that simple. I mean, it doesn't necessarily seem like a simple idea, but all it is a graphical solution to a real-world problem. The other thing is that if you have a pipe, if you think about it this way, if you have a pipe that, I'm trying to find a decent pen here to write with, that other one's too thick. If you have an energy line that looks like this, and you have a pipe that looks like this, you can tell, just sort of intuitively, that water will run in this pipe. Well, what happens if instead, let's just say the energy line looks like this, we still have no friction, lucky for us, right? What's going to happen if your pipe raises in elevation above the energy line? Well, the answer is that you will not flow water. The water will actually run backward at that point. And it's actually a little bit worse than this diagram suggests because you do have friction. So although we talk about the energy line being constant, the energy line actually goes down in elevation based on the line losses, on the roughness of the pipe and the size of the pipe. And all those things are generally available to you in modeling or simulation software, which we'll talk about farther on down the line. So section 3.8 talks about restrictions on the Bernoulli equation. The Bernoulli equation is one of the most well-used and, I would say, poorly used equations in engineering history. The problem with the Bernoulli equation is it's very simple mathematically, and so we tend to want to use it even when it's not valid. We can gin up the equation to take into account different corrections. However, in its basic form, P over gamma plus V squared over 2G plus Z equals a constant, or equals the total head, there are many, many restrictions. First of all, we are only talking about incompressible flow. We are also talking about inviscid flow. In other words, we have to be in the region of flow where viscosity does not matter, that we're not going to be taking into account those shearing effects that we get, especially at the edge of a pipe. But also some fluids are just so viscous that we have to take them into account everywhere in the flow stream. We also are assuming that there is no head loss. In other words, due to those line losses, friction, etc. And also that there is no head gain. This is only valid if there is no pump or turbine or something else putting energy into the system, no friction, no line loss, taking energy out of the system, no viscous effects, and no compressibility. So what that means for us is, therefore, Bernoulli is easily misused. Now, if you recall, when we started talking about the Bernoulli equation, we said that we were starting with an differential equation, and it looks something like this. And we actually started with the summation of forces along a streamline is equal to mass times the acceleration, or the dv dt, or the v, this is ds dt, dv ds, right? So in other words, we start with Newton's second law. Start with Newton's second law. So we always have to remember, especially the fact that we have an integral here. So if we have a situation where we are not incompressible, where we have to take into account the compressibility effects, then we have to execute this integral. So that means that we would have to have rho as a function of p in order to appropriately use the Bernoulli equation. All right, so that actually ends the material for chapter 3, and I would like to do problem 398, just to sort of get you started with this process. Now, if you take a look at problem 398, we are in your textbook on page 157. And that actually refers back to problem 360. So what it asks us to do is, excuse me, I'm trying to do two things at once here, which is never a good idea. But basically, what we're doing then is we are referring back to a problem, 360, which I'm not sure, I'm going to check your website here. I wanted to double check if I assigned that for homework or not. I guess I can do that in my folder here. So let's see, homework for chapter 3. Did I assign problem 360? I'm just pulling this up on the Podium PC right there. So I did not. So we're actually going to have to do problem 360 before we're able to draw the hydraulic grade line and the energy line for that problem. So let's go back. Let's just write our instructions. Draw 398. Draw the energy line and the hydraulic grade line for the flow problem in 360. Right. So let's turn back in the text to problem number 360. And what we have in 360 is a water flow from a large tank. And we have an atmospheric pressure of 14, sorry, I have too many books here. We have an atmospheric pressure of 14.5 psia. And let's see what else. A vapor pressure of 1.6 psi. All right, so we already know from that discussion that we can't go below vapor pressure or we're going to get that cavitation effect. We talked a little bit about that last time. So it says, if viscous effects are neglected, at what height h will cavitation begin? And to avoid cavitation, should the value of D1 be increased or decreased? All right, so beginning on working that problem, instead of answering the questions right away, let's go ahead and draw our picture and do an analysis of this problem using the Bernoulli equation. All right, so what we have is a tank of water, and we're drawing it to the midline of this funny squiffy pipe that has a couple of changes in diameter. Okay. And the tank goes below, and here at the midline we have this distance h to the top, where we're told that the surface is at the atmospheric pressure of 14.5 psi. All right, so we have h. We're told that these diameters, we're calling these D3, both equal 4 inches. And we have D1 right here is 1 inch. And at the outlet, right here, we have D2 is equal to 2 inches. All right, now I'll get my left hand out of the way so you can see what we've got. So all I've really done is reproduce all I've done is reproduce the drawing in your book. Okay, so I am further told that the vapor pressure is 1.6 psi, or psia. So I'm going to neglect my viscous effects. We're talking about water, and we don't have a pump. We're going to assume no line loss. So we can say then that the Bernoulli equation is applicable in its unadulterated form. So what that means is if I find my total energy here at point 0, that it will be equal to my total energy anywhere. I can say 0.1 because that's really the diameter that I'm interested in, and it's also going to be equal to the total energy at 0.2. So let's go from 0 to 1, first of all. So I can say P0 over gamma plus V0 squared over 2G plus Z0 is going to be equal to P1 over gamma plus V1 squared over 2G plus Z1. All right, now if I look at P0, I'm exposed to the atmosphere, so my P0 is going to be 14.5. My P1, in order to avoid cavitation, has to stay at 1.6 psi or above. My Z0 is h distance above Z1, so I could say that Z0 is equal to h if Z1 is my datum equal to 0. And my velocity here is also going to be equal to 0. So I'm going to put this toward the top. I've got too much nonsense here. Let me get some of these papers out of the way. Okay. So let me put my drawing toward the top of the screen. There we go. And we'll eliminate some of our data. So we have this and this. We know that this is equal to 0. Using my datum, we could say that this is equal to 0, and this is going to be equal to h. So if we rewrite this equation, we can say P0 over gamma plus Z0 equals P1 over gamma plus V1 squared over 2G. And then we can plug in some of our values. Or let's go ahead and, I should put that for H. Let's go ahead and just solve this for H. H then is going to be P1 over gamma minus P0 over gamma. So we have a common denominator. Just do that. Plus this term. Right. Now, we need another fact as well. We know that Q is going to be constant. The flow rate is going to be constant. Truly, in principle, it's our mass flow rate that is constant, but since it's incompressible, since gamma is a constant, or rho is a constant, then Q is also a constant. And Q is going to be equal to A times V. Right. All right. So if we go from point 1 to point 2, so since we're looking at this, we can say A1 V1 is equal to A2 V2. And that gives us another equation to work with. Or we could solve for V1 in terms of V2. It's the ratio of A2 over A1 times V2. All right, now we could further assume that this point 1, I think I just lost on the screen, point 1, that the pipe is circular, and point 2, the outlet is circular. So A2 is going to be pi d2 squared over 4, and A1 is going to be pi d1 squared over 4. And so fortunately, the pi's and the 4's cancel out, and we just get an expression that tells us that V1 is going to equal d2 squared over d1 squared times V2. All right, so we also know, if we think about it, if we look at this expression here, P0 is exposed to the atmosphere, and P2 is also going to be equal to 0 because we're open to the atmosphere. So it's going to, or excuse me, not 0, it's going to be 0 gauge, but it's going to be equal to P0, or atmospheric pressure, because we are open to the atmosphere. And we can also see that Z2 is on the center line of H, and the way we've defined our datum, Z2 is also going to equal 0. All right, so that's a lot of information to take in, but we can then equate what's going on between P0 and V0. Eliminate those terms. And if we recognize that P2 is equal to P1, gammas are equal, those terms will go away. And also recognize that Z2 is equal to 0. We can actually say that V2 squared over 2G is equal to this, but it's also going to equal H. All right, so I just kind of did that quickly because this is taking a lot longer than I had anticipated it. All right, so if I reduce the equation and I combine them again, get another piece of paper. Okay, now you might have to rewind on this to make sure that you get that, because it's a little bit complicated. Not difficult, but we're using the equation at two different points. We're using Bernoulli's and equating everything at two different points. Okay, and the equation's reduced to this. V2 squared over 2G is equal to H. So there's sort of the end game of that particular formula. All right. So we can take these ideas and combine and come up with the expression that H is going to be equal to P1 minus P0 over gamma, plus the quantity D2 over D1 to the fourth times H. And if we do through a little bit of manipulation, we can solve for H. We'll have to bring this term over here, divide by this, right? Or excuse me, take 1 minus this, and then multiply that through by H, and then divide the other side. So the equation actually, it's a little bit of algebra. I'm switching these sides because it's actually a negative. But we get D2 over D1 to the fourth minus 1, because remember it was actually going to be 1 minus this. So when this term switch, the sign over here on the top switches as well. And if you plug in the numbers, we know that P0 is 14.5 psi. We know that P1 has to stay at least 1.6, and that's going to be in PSI. To get it, let's see, PSI is a pound per inch squared. We're going to have to convert that back to feet in order to keep our unit set. On the bottom, we have gamma of water, which is 62.4 pounds per cubic foot. And then this is going to be a dimensionless term because it's 2 inches divided by 1 inch raised to the 4th power minus 1. So the entire parenthetical quantity here is dimensionless. And up here we're going to have pounds per foot squared over pounds per foot to the 3rd cubic feet. So we're actually going to, pounds will cancel out, inches squared will cancel out, feet squared cancels against feet squared down here. We're left with feet. And so we get H, and if you do the numbers, if you run the numbers, you get on top 14.5 minus 1.6. So that value is 12.9. And on the bottom, 2 raised to the 4th power, subtract 1. 16 minus 1 is 15. Multiply that by 62.4, and that value is 936. Okay, and then this one's multiplied by 144 because of that conversion factor. So I get 12.9 times 144, divide that by 936, and I get a height of 1.985 feet. It's quite a few significant digits. I would really run with 1.98. Now let's think about whether it should be 1.98 or 1.99. Okay, the answer is, if we get higher here, we're going to have more energy associated with the total flow regime, which means that here we're going to have more energy, which means that we can stand more pressure head. So the answer is H, as H increases, we would have to increase D1 and decrease D2. To avoid cavitation, D1 should be increased, D2 should be decreased, okay, to avoid cavitation. All right, so that's problem 360. Now, to work 398, we're going to draw the energy line, which that's actually kind of easy because we start at a height, a pressure of 14.5 psi. And if we take 14.5, P over gamma, divided by gamma, we have 14.5 psi over the value of gamma for water. And when we resolve the units, we'll have the energy line. Okay, so basically what we have then is well, we could also just solve for H, is what I was thinking. We have an inviscid flow, we still have all of that validity. But if we found out what H is, we obtained this value. So that H is actually our energy. So H is, let's say, 1.98 feet for the problem as it's set up. And so if we go back to our original drawing, the energy at this point, remember, because we're open to the atmosphere, so P is equal to, if you think about P over gamma plus V squared over 2G plus Z. At this point, there's no velocity. Well, we're at P, but we're open to the atmosphere, so if we're talking about it in terms of gauge, our Z is whatever that value is, 1.98 feet. So our energy line is just a straight line at that value. Now, in this pipe, we're going to have a velocity. In this pipe, we're going to have a velocity. In this pipe, we're going to have a velocity. And as we do that, we're going to have to subtract V squared over 2G from the energy line. So we need to know the velocity in, well, let's say the velocity 3 is the way that your authors call it out, because the diameters here are the same. Let's also find the velocity in 1, and then we could find the velocity at 2. And I think some of this information we've already found in the problem. Maybe we haven't yet. So let's go ahead and just solve for it. Okay, first of all, let's go ahead and find our Q, our flow rate, because we know that Q is equal to V times A, and because we have the cross-sectional area of each of those, we can solve, after we find our Q, we can take that and divide it by A and solve for the velocity. Or we could, I'm just looking at this, we could also go backward, but. All right, well, if we continue with that, let's go ahead and think about this. Here in 3, I wish I could keep this picture up here while I'm doing this. There's too much stuff. Okay. The Q in both of them is the same, so we can say Q in part 3 is equal to Q in part 1 plus Q as it exits at 2. So if we look at the 4-inch pipe, we can say that this V is going to be equal to Q, which is a constant, over the area of pipe 3. This is Q, which is a constant, over the area of pipe 1, and Q here over the outlet area. So we can equate this to that ratio that we talked about with the diameters. So we could say that V1, this is where I came up with this equation when I was working this through, V1 squared over 2G is equal to D2 over D1 to the 4th times H. Now we have everything in this problem except for V1. So we can solve for V1, then we can solve for Q, then we can use that here with those areas to find each one of those values. So let's say V1 is equal to 2G, V1, now I'm going to have to get square root here, is equal to the square root of 2G times D2 over D1 to the 4th times H. I'm going to pull this term out as a square. Okay. And then I just have inside 2G times H. And based on that height of 1.98 feet, let's go ahead and solve for that. So V1 is equal to D2, which is 2, over D1, which is 1, raised to the second power, times the square root of 2 times G, we're in feet, 32.2 feet per second squared, times my height, which is 1.98 feet. All right, so first of all, I can see from my units, this is dimensionless. Here I'll have feet squared per second squared. When it comes out of the radical, it'll be in feet per second. So we get V1 is equal to 2 squared, which is 4, times the square root of this quantity, 2 times 32.2 times 1.98. So that's the square root of 127.5. And if I find the square root of that, I get 4 times 11.29, which is 45.17 feet per second is my velocity at 1. All right, now using these relationships, let's go ahead and find my Q. So using this, I know that V1 times A1 is equal to Q. So 45.17 feet per second times the area of 1, which is pi d squared over 4, pi d1 squared, and d1 is 1 inch. Okay, let's do this. We need this in feet, so I know I have to divide by 12, so let's say 1/12 foot pi d squared over 4, right? And so I get 1 over 144 times pi, or 3.14 divided by 144. That's this information divided by 4. And that quantity multiplied by 45.17 feet per second. And my value is 0.246. And that's going to be in cubic feet per second. Okay, now that's a constant, isn't it? Because this is incompressible flow. So that means that my velocity here, I know this velocity, 45.17 feet per second. This velocity is going to be 0.246 cubic feet per second divided by area 2, which has a diameter of 2 inches. Let me pull this paper down. So I'll have a diameter of 2 inches on my outlet. So it has a radius of 1. So instead of using diameter, I can say pi r squared, which is pi times 1 inch squared. And that's going to be 1/12 of a foot squared, right? So then I got feet squared, feet, so this is going to come out in feet per second. So I have 0.246 divided by pi. And then that number, I have 1 over 144 here. It's actually going to be multiplied by 144 to get the value. And my velocity is 11.28 feet per second. Okay, now does that make sense? Think about this. Here in point 1, we have a very narrow conduit. So does it make sense that we would have a higher velocity here? It certainly does. It's going to have to go through faster, and then it will slow down right here. So then my Q up here, still the same, 0.246. I know I'm going to have to multiply it by the 144 to convert, and then it's going to be pi times however many inches the radius is. So that's 4-inch diameter, so it's 2 inches radius. And so my velocity at point 3, 0.246 times 144 divided by pi, and divided again by the radius, which is 2, and we have a velocity of 5.64 feet per second. Okay, and once again, it makes sense. This is quite a bit larger than this, quite a bit larger than this. It's a huge conduit, so we have a smaller velocity in those values. All right, so what we're going to have, I'm going to clean up this picture a little bit. We have the tank. We have the pipe, the narrowing, the widening, and the outlet. And the velocity changes as we change size of the pipe. So what that means is the energy line stays the same at 1.98 feet. But to find the hydraulic grade line, we need to subtract off v squared over 2g. Right. So we're going to have a different velocity here, and the same, the velocity is going to be here and here. Velocity is going to be different here. So let's go ahead and take a look at 3. The velocity at 3 squared over 2g is going to be that value 5.64 squared over 2 times 32.2. This is going to be feet squared per second squared. This is feet per second squared. Second squared cancels out. I'm left with feet. And that gives me a height. So that will be correct. So this will give me an elevation in height. So I take 5.64, square it, divide by 2, and divide again by 32.2, and that value is, my velocity head is 0.49 feet. What that means is here, my hydraulic grade line is going to be 0.49 feet below my energy line. Or the value here, hydraulic grade line, is going to be 1.98 minus 0.49, which is 1.49 feet. Okay? What happens here? I have a higher velocity. That's 0.1. And my velocity at 1 I found to be 45.17. So when I do this, I'm going to take 45.17 squared and divide it by 2 times 32.2. Don't need to redo my units because I've already done that. So I take 45.17 squared and I divide it by 2, and then I divide it by 32.2, and that value is 31.68. Well, that's really interesting, isn't it? Because according to that, my energy line right here is going to be way below the pipe, or my hydraulic grade line, which is still fine. But that means that my hydraulic grade line is going to be at 1.98 feet minus 31.68 feet. And that value is negative 29.7 feet. Okay, so that means that in this section, that's going to drop way down here. Hydraulic grade line is equal to negative 29.7 feet. Okay, we know that the velocity here is the same as the velocity here. So we know that my hydraulic grade line will be at the same point, right? But then when we get to 2, the velocity at 2, we know is 11.28. So we take 11.28 and we square that number, divide it by 2 times 32.2, and we get 11.28 squared divided by 2 and divide again by 32.2, and that value is 1.97. Well, that is just very slightly less than my energy grade line. So what does that mean on the outlet? It means we go practically to 0. So my energy grade line right here drops to this value. My hydraulic grade line is approximately equal to 0 at that point. All right. So 3.98 took us a long time to work, but that's the basic approach. All right, so that does it for Chapter 3. I've posted your homework to our Moodle site, so you can get started, and we'll see you later for Chapter 4.